Okay, very good. Welcome everyone to the next session of the workshop. Today we have Joachim Kopp. Joachim got his PhD from Max Planck in Heidelberg, and then he moved to Fermilab. After that, he came back to Europe as a leader of an Otto Hahn Junior Research Group in Heidelberg. And from there, he took a faculty position at the Mainz Institute for Theoretical Physics. Right now, he's on leave and he's at CERN since 2018. And his interests are a little bit of everything. He does a little bit of everything, but especially neutrino physics and dark matter. And today he's wearing his neutrino hat and he will be speaking about sterile neutrino anomalies. So please, Joachim.
Well, thank you very much for the invitation, and thank you very much for the nice introduction. I'm, of course, sad that I can't be there in person. But yeah, I hope that one day we'll also have Christmas workshops in person again. So the topic that I'm going to talk about today, the short baseline neutrino anomalies, is actually a topic that I rather frequently give talks about. The thing is, so much has changed in the field in the past few months that it's still a rather new talk, because most of the slides that I used to show last year, for instance, are totally outdated, so had to be replaced. And so I'm going to focus in this talk now really on the recent developments that have happened in the last few months. So what's the context? Well, the overarching goal of much of what we do in neutrino physics is to do precision flavor physics. You're familiar with that from the quark sector. There's this famous plot shown here on the left-hand side, which shows the unitarity triangle in the quark sector, which kind of summarizes our understanding of CKM matrix. And what's really amazing about this plot is how lots of different observables play together to narrow down the position of the tip of this triangle to this tiny yellow region here at the center. We'd like to do the same in neutrino physics, but we are not quite there yet. So the plot on the right-hand side is from global fit to neutrino oscillation data. And I realized that I should also have updated this plot because there's also newer versions of new fit, of course. But the general picture is still the same also with the newer fits. There's much more uncertainty still. In particular, we have a rough idea of how far the tip of this triangle is from the origin, but we don't know very well in what direction it is located. And that's just a reflection of the fact that we don't know whether there is CP violation in the neutrino sector. So that's one of the big goals to hopefully be answered in the next 1 or 2 decades. Okay. So how do we do this? We usually do this with neutrino oscillations. Neutrino oscillations are based on the fact that neutrino mass and flavor eigenstates are not the same. So the states that have a definite mass and a definite energy are not the states that we see in weak interactions. These are the flavor eigenstates. And the two bases are related by a unitary mixing matrix, which we think is a 3×3 matrix because we think there are 3 neutrino flavors in nature. About that mixing matrix in the neutrino sector is generally parameterized as a product of 3 two-dimensional rotation matrices. And the mixing angles of those rotation matrices are reasonably well known. We know that one of them is large, close to maximal, that a second one is large but not maximal, and that the third one is small but non-negligible. And finally, there is the CP violating phase, and we don't know yet what the CP violating phase is. Now, this physics is usually done in what's called long baseline experiments. Baseline here refers to the distance between the neutrino source and the neutrino detector. And the reason one needs a large distance is because one wants to observe neutrino oscillations. And neutrino oscillations take some time to develop, so we need to give the neutrinos that time. And this means we need to allow them to travel for sufficiently long. Here, however, I'm going to focus on experiments with rather short baseline. So you may ask, why would anyone do short baseline experiments if the thing to do to answer these fundamental questions is long baseline neutrino physics? Well, some of the experiments that I'm going to talk about were built or planned before the standard model oscillation lengths were actually known. So at the time, we had no idea what the neutrino masses would be and if they would be non-zero at all. And so people tried to look for oscillations at all kinds of different length scales. And of course, they started at short baseline because that's where it's easiest, because that's where you get the largest event rates. And some of the experiments that I'm going to talk about are motivated by physics that does not directly have to do with flavor mixing. For instance, it can be motivated by things like cross-section measurements. And the reason I'm in particular talking about short baseline experiments is because some of those have given us some anomalous results that we don't understand yet. And I hope to shed some light on those in this talk. So I'll first introduce all the different short baseline anomalies. Then I will focus in particular on the mini-Boone anomaly and will tell you about why that anomaly is interesting and what could be possible standard model explanations. And in the very end of the talk, I will talk about the possibility that these anomalies are explained by sterile neutrinos. So let's start with an anomaly that is based on actually rather old data, but relatively recent theory. So it's called the reactor neutrino anomaly. And it's the statement that the observed neutrino flux from nuclear reactors is about 3.5% below the theoretical prediction. This result came about in 2011, not because we had substantial new data at that point, but because we had substantial new theory at that point. So in 2011, two different groups re-evaluated the theoretically expected neutrino flux from a nuclear reactor and came to a result that was generally considered state of the art, but which was in disagreement with the data that had been collected previously, and it amounted to this deficit. At the time, this caused a lot of excitement because people proposed the possibility that some of the electron neutrinos from a nuclear reactor may oscillate into a new sterile neutrino state on the way from the reactor to the detector. Then these sterile neutrinos would be undetectable with the usual technologies, and therefore they could explain this deficit. Now, what you see in this plot here is a summary of the anomaly. The horizontal axis is the distance from the reactor core. The vertical axis is the event rate relative to the expectation. And the data points are from all kinds of different reactor neutrino experiments that have been done throughout the history of neutrino physics. And as you can see, the data points cluster well below 1. And that's just a reflection of this deficit. Now, the thing is, these theoretical predictions from 2011, they were, of course, not first principles predictions. This is nuclear physics. If you want to get percent level predictions of a system as complex as a nuclear reactor, then you need to take some input from data. And some of the data that these predictions were based on were measurements of the beta spectra from uranium fission. So the experiment that was done was you take a thin foil of, say, uranium-235, you irradiate it with neutrons to induce fission, and you look at the spectrum of the electrons that comes out. And then, very roughly speaking, in a nuclear beta decay, any energy that does not go into the electron goes to the neutrino. And so you use that to infer, in a rather non-trivial way, the neutrino spectrum from this electron spectrum. Now, this data on the electron spectra from nuclear fission, this has recently been updated. And with this updated data, also the theoretical prediction of the reactor neutrino flux was redone. And wait, where is, yeah, so here's the plot. So let me flip between those two possibilities. Here is the old prediction with the old data. Here is the new prediction. So you see that with this measurement, the anomaly is gone. So I think we can put a check mark behind the reactor anomaly. Apparently, it was due to a systematic bias in the old 1980s level data on electron spectra from nuclear fission. So personally, I consider this reactor flux anomaly resolved. Now let's stick to the nuclear reactors. More recently, people have realized that there is an uncertainty in the reactor fluxes, so they have paid more attention to reactor neutrino spectra. The idea of this new generation of experiments is that you take measurements at different distances from the nuclear reactor and then consider the ratios between those measurements. That way, your measurements are completely independent of the initial neutrino flux. But if there is something like neutrino oscillations, then you would still see it. In particular, you would see it as a wiggly signature on the spectrum. Here is a result that is based on data from the NEOS experiment. And you can indeed see, yeah, there is something that can be interpreted as wiggles. And so if you wish, you can use these wiggles and see if they are consistent with an interpretation in terms of neutrino oscillations. Once again, the idea would be that there is a sterile neutrino and that on the way from the reactor to the detector, the active neutrinos oscillate into sterile neutrinos. And since this is an energy-dependent process, you would sometimes see a relative flux deficit and sometimes a relative flux enhancement between the measurements you are taking at those two different baselines. Here is a fit to this kind of data. This is from a paper by Jeffrey Berryman and Patrick Huber from last year. The green contours here is what they get from a global fit to all available reactor data of this type. And as you can see, at relatively low significance, there are some closed regions here. There's also this blue result. This is from an experiment called Neutrino 4, which claims an observation of these spectral wiggles at larger statistical significance. But this result has been called into question for other reasons, so it's shown separately here. So overall, I would say these reactor spectra, yes, there are maybe some hints, but it's not very significant. And I could still imagine that there may be other explanations of this anomaly. So I'll put a question mark behind it. It's not ultimately resolved, but I think it's not something that should cause us sleepless nights at the moment. So let's move slightly away from nuclear reactors, but stay with the electron neutrinos. As you know, electron neutrinos are not only produced in nuclear reactors, but they are produced in essentially any nuclear beta decay. So there have been experiments that used intense radioactive sources to produce neutrinos. The idea is you take some material, you irradiate it inside a nuclear reactor to activate it, and then you have this material that is very, very highly radioactive. You pack it in a shielded container, you transport it close to your neutrino detector, and you let it sit there for a while, and you see what comes out. Ideally, the shielding absorbs all the neutrons and electrons and whatever comes out of the decays, but the neutrinos, of course, get out and can be detected. Because those neutrinos are typically relatively low energy, this is best done using radiochemical techniques. So a reaction that has sometimes been used is this one here, an electron neutrino captured on gallium-71, converting that nucleus into germanium-71 and an electron. You have a detector that contains gallium-71, you let it sit there for a while, and then after some time, you extract maybe a handful of germanium nuclei that have been produced inside the detector. That sounds like a search for a needle in a haystack, but it can be done. And by doing this, one again finds that there are fewer neutrinos observed than predicted. The historic measurements of this type are shown here in this plot. There's 4 data points, and all of them are significantly below 1. And altogether, this amounts to maybe a 3 sigma deficit. And once again, the reason this caught people's interest is because this could in principle be explained by disappearance of electron neutrinos into a sterile state. The thing is, if you look at these data points, these are really substantially below the prediction. This is not a few percent effect. This is a 20% or 10% effect on average. So this would require rather large mixing between the electron neutrinos and the sterile neutrinos. But I should say this is, until the recent reactor measurement, this is not per se ruled out. Now, recently, this anomaly has in fact been reinforced. There was a new experiment called BEST, the Buxan experiment for sterile transitions, that again uses this radiochemical technique. So looking again for that reaction here, neutrino capture on gallium. The novel thing about BEST is it uses 2 independent target volumes, as shown here, the inner target and the outer target. And the hope was that if there is an oscillatory effect, then the deficit that is observed might be different in the inner region and in the outer region. But what BEST has given us is they do observe the deficit, but the rate is the same in the inner and outer region. Oops, wait, I don't have a plot of that, unfortunately. One can argue, of course, that the radiochemistry, so this extracting the needle from the haystack procedure, is still similar in BEST as it was in previous measurements. So if there's something wrong with that procedure, if for whatever reason you sometimes miss a few of the germanium atoms that you've made, then this would suffer from the same systematic bias. One of the reasons it is not terribly likely that there is such a systematic bias is that those same experiments have also been used to observe solar neutrinos, and their measurements of the solar neutrino flux agreed with measurements in other experiments like Super Kamiokande and SNOW and so on. So given that we think we understand the sun, given that we think we understand solar neutrinos, those solar neutrinos can be used to cross-calibrate the radiochemical extraction method and give us some confidence that there's not just a third of the germanium nuclei being missed by this procedure. So that anomaly still stands. BEST has significantly increased its significance, so it's now way above 3 sigma, but there's no explanation at the moment. And in particular, since the deficit from reactors that was called the reactor anomaly now appears to be gone, there is a tension even within the new E sector. So the radiochemical experiments observe this deficit, the reactor experiments do not. So I would say that one is also still unresolved. Now let's move to accelerator-based neutrino experiments. The oldest one of those that I'm going to talk about is LSND. LSND stands for Liquid Scintillator Neutrino Detector. That was an experiment at Los Alamos National Laboratory that ran in the 1990s. In this picture here, there is a beam of protons coming in from the left and hitting a target, which is called the beam stop here. So this is where the protons get absorbed, and as they are absorbed, they make lots of pions. The target is thick, so most of those pions do not make it out of the target. Instead, they slow down until they are at rest, and they eventually decay at rest. When they decay at rest, they make neutrinos. They make muoneutrinos, they make electron neutrinos, and they make muon antineutrinos, but they do not make electron antineutrinos. And so the idea behind the experiment was to look for muon antineutrino to electron antineutrino conversion. That was at a time when neutrino oscillations had not been observed yet. So this was a search just for standard neutrino oscillations. The source detector distance was of order 30 meters, which as we now know is way too short for standard neutrino oscillations, but at the time that was not known. And one of the reasons this is an interesting channel to look at is because electron neutrinos have a rather clean signature. They do inverse beta decay, so you get a prompt positron and a delayed neutron. And this coincidence is excellent for background suppression. So here's the famous LSND result. The horizontal axis is the baseline divided by the energy. That's a bit of a funny way of showing a spectrum, but since that is the quantity on which the oscillation probability depends, it's probably reasonable. And the vertical axis is the number of events. The red and green histograms are the expected backgrounds. The blue histogram is a fit to the data. And as you can see, that fit to the data is significantly above the background prediction. So there is a 3 sigma excess of electron antineutrinos that at the time had been interpreted as muoneutrino to electron neutrino conversion. We now know that that cannot be neutrino oscillations in the standard model, but people have entertained the possibility that if you add an extra 4th neutrino to the model, then you can get these transitions even over the short distances seen at LSND. Once again, LSND is an unresolved anomaly. And as far as I know, no one has any really good leads as to what it could be. So if you have an unresolved anomaly, what do? You build a new experiment to test it. And that was done in the form of the mini-boon experiment. The idea behind the mini-boon experiment was specifically to test the possibility that LSND is due to neutrino oscillations. The source and detector are quite different. The source is at much higher energy, so it receives high energy protons from the Fermi-Lab booster. Those hit a target. In the target, you make lots of pions, but this time the pions are not stopped, but they are focused in the forward direction by a magnetic system. And then they are allowed to decay in flight. Then the neutrinos from these decays in flight travel through a few hundred meters of dirt, and eventually they are detected in a big tank filled with liquid scintillator. But the main signal used in LSND is in fact not the scintillation light, but Cherenkov radiation. And here's what Mini-Boon has found. So in fact, Mini-Boon has found an excess as well. That excess is concentrated at low neutrino energy. So what you see here in the plot on the bottom left is neutrino energy versus event rate. You can see that at high energies, the data is more or less consistent with the background prediction, whereas at low energies, there is a really significant excess. Statistically, that's a 4.5 sigma effect. If interpreted in terms of neutrino oscillations, that excess is consistent with LSND, but inconsistent with the standard model again. So the comparison between Mini-Boon and LSND is shown here on the right-hand side. This is a plot that shows the, let's say, the effective mixing angle between muon and electroneutrinos that would be induced by the presence of this sterile state. And the vertical axis is a measure for the sterile neutrino mass. The blue regions are from LSND. The unshaded colored ones are from Mini-Boon. And as you can see, there is some significant overlap between. So those two experiments among each other appear to be consistent and appear to confirm one another's findings. Now, there's a lot to say about Mini-Boon, and in fact, that's what I'm going to spend most of my remaining time on. And I will start by talking about possible standard model explanations for Mini-Boon. Of course, I don't have a standard model explanation for Mini-Boon readily available. So instead, I'm going to show you some of the challenges involved in coming up with such a standard model explanation. So when we talk about standard model explanation, of course, that means some misestimation of one of these many backgrounds. If you look at the spectrum here, you realize that Mini-Boon is doing a measurement on quite a large background, and that background is coming from lots of different sources. I'm not going to talk about all of these sources here, but one background I want to pick out just for illustrative purposes is the one shown in light brown here, which is labeled delta to gamma n. One could do a similar discussion about the other backgrounds, but I'm just picking out this one just because for a long time I had considered that one to be the most likely culprit for the anomaly, but now I've had to change my mind. So that background is based on the production of a delta resonance in neutral current neutrino interactions. So remember that Mini-Boon has a very large flux of muon neutrinos and are looking for an excess of electroneutrinos. Now, because there is this large flux of muon neutrinos, which are not supposed to show up in this search at all, some of these muon neutrinos will do a neutral current interaction. And as they scatter off a nucleus, they may excite that nucleus to one of the hadronic resonances. And the lowest lying one and the most likely to be excited is the delta 1232 resonance. Now, most of the time, the delta 1232 decays to a pion and back to a nucleon. The pion is detected in Mini-Boon, but it wouldn't show up in this search for electron-neutrino appearance here. The thing is, there is a rare decay mode of the delta resonance to a photon and a nucleus. And given the detector technology that Mini-Boon is using, they are not able to distinguish a single photon from a single electron. Now, a single electron, however, is the signal they are looking for. If you're looking for muon neutrino to electron neutrino conversion, then the signal you're looking for is electron neutrinos. And an electron neutrino shows up in this kind of detector as a single high energy electron coming out of nowhere. And what I'm saying now is that a single high energy photon coming out of nowhere is completely indistinguishable from the signal in this detector. So clearly this type of process makes a contribution to the background in Mini-Boon, and therefore it shows up in this plot. Now one can argue whether this background has been correctly estimated, and for all we know it has been correctly estimated, but I still want to point out some of the caveats one may encounter when trying to estimate this background. Now you might argue, well, in principle, we can measure the rate of delta production by looking for the dominant decay mode, right? I said that most of the time the delta resonance decays to a pion. Pions can be identified. So by doing an analysis on the pions in Mini-Boon, we can in principle measure the rate of delta production. Now that sounds easy, but in fact, there's a lot of complicated physics involved that has to be taken into account. And that's because this delta resonance is not produced just in vacuum, but it is typically produced inside an atomic nucleus. That means that as that pion from the delta decay travels out of the nucleus, several things can happen to it. Either it can hit another nucleon and excite yet another delta resonance. In that case, the probability that one of the two delta resonances decays through this rare radiative decay mode is enhanced. So that contributes roughly a factor of 2 enhancement to this estimate. The other possibility is that the pion is simply absorbed and never leaves the nucleus. And then, of course, it can't be detected. In that case, your control measurement of delta to pi decays would be suppressed by roughly a factor of 2. So the Mini-Boon collaboration, of course, were aware of this and took this into account in the form of a correction factor that they applied in their analysis. Now, one can argue whether that correction factor is the most sophisticated thing one can do, but as we'll see later, it's probably okay. But this is just to highlight one of the things that can go wrong. There's another thing that I would like to mention here, namely this radiative decay mode. There's a question about how well we know this decay mode. If you look in the particle data group, if you look in the PDG, they quote an uncertainty of order 20% for that decay mode, mostly because there's no direct measurement of that decay mode. Now, personally, I'm not sure that that may be one of those really, really overly conservative estimates that sometimes show up in the PDG, because what we can do is we can measure the inverse process. We can irradiate nuclei with gamma rays and look for excitations of the delta resonance. That way, we can measure the amplitude for this transition. And once we know the amplitude, we can also compute the decay rate. And that would suggest that maybe the uncertainty should only be somewhere at the percent level. But let's for a moment assume that really this very large uncertainty quoted by the PDG is the right one. Then we've done some test runs in a Monte Carlo simulation, predicting just this one background. The horizontal axis is again the neutrino energy. The vertical axis is the number of background events in this channel. The gray histogram here is the official Mini-Boon prediction for that background. The blue histogram is our reproduction of this with a different Monte Carlo tool. And the hatched region here shows by how much our prediction varies if we allow the branching ratio of the delta resonance and two other heavy resonances to vary within their 2 sigma intervals from the PDG. Now, let me emphasize, this is probably a way too conservative thing to do. So I'm not claiming that the uncertainty on that background is actually that large, but it just shows that these backgrounds can have a substantial impact. Now, fortunately, Mini-Boon is not on its own. So recently, the Micro-Boon collaboration has released its first results. Micro-Boon is a detector that's basically in the same location as Mini-Boon, so it sees the same neutrino beam at the same baseline, but it's a different detector. So it's not based on liquid scintillator or Cherenkov radiation, but it's a liquid argon time projection chamber. As such, it has very good event reconstruction capabilities, and in particular, it is able to distinguish electrons from photons. So it is able to distinguish a true electron neutrino appearance signal from a fake signal due to any source of single photons. So here you can see such an event display from Mini-Boon versus Micro-Boon. On the right-hand side is Mini-Boon. You can see that there's basically this blurry Cherenkov ring. That's all you have to work with. And on the left-hand side, a Micro-Boon event where you can really nicely see the tracks. You can measure the DEDX along the track. You have very fine spatial resolution. So it's really a different kind of detector. And here is what Micro-Boon found when they searched for delta to gamma n. So they did a search where they looked specifically for single photons plus nuclei, because they can also see the recoil nuclei or nucleons in many cases, specifically to test the hypothesis that the Mini-Boon anomaly was due to a misestimate of this background. And as you can see here, their data agrees quite well with the standard model prediction. That's the black line here, and it's even a little bit low. On the other hand, in order to fully explain the Mini-Boon anomaly, one would have expected a result that's here at the level of the orange dashed line. So that's clearly not the case. So microboon quite strongly disfavors single photons from delta decay as an explanation for the mini-boon anomaly, confirming that the background estimate that the mini-boon collaboration was working with all along is probably correct, at least in this channel. Now, I should mention one caveat here, namely, this was a search only for delta to gamma n. So this was a search for single photons specifically from the decay of a delta resonance. If there's another single photon process, another process that makes such high energy photons, that could still be a viable explanation for mini-boon, and that would not have shown up in this particular analysis by microboon. I'm not aware of any such process, but if there is one that we've missed for whatever reason, then it might still be viable. Of course, microboon will eventually also do an inclusive single photon search that then might pick up such a background as well. Now, let's consider now the possibility that what we are seeing there is really sterile neutrinos. I will show that this is a rather unlikely possibility at this point, but let's still discuss it. So first of all, we have to take into account once again what microboon has to say on this hypothesis. So if the mini-boon axis is really due to an axis of electron neutrinos in the beam, then microboon could see those as well. That's what the detector was primarily built for. So the signature in microboon would again be the appearance of a single high energy electron. The difference is that microboon would also see the recoil nucleons typically. So microboon has done several different analyses looking for single electrons, either inclusively or with exactly one single nucleon, or with a single nucleon and no pions, or with no protons, no pions. And none of these searches sees a significant excess. So what's shown in this plot here is the observed event rate over the predicted event rate, and all of the data are consistent with one. Whereas in order to explain the mini-boon axis in full, we would have expected the data points to follow these red lines here. And you see that in particular in the search on the left-hand side, the one for a single electron and a single proton, which corresponds to charged current quasi-elastic interactions, there is no excess. And also in the inclusive search on the right-hand side, that's also quite sensitive due to the small error bar, there's also no excess whatsoever. In fact, once again, there's even a slight downward fluctuation observed in microboon. Now, microboon have only shown their results at this level, but we've turned this into a sterile neutrino fit in a recent paper with Carlos Arguelles, Pedro Machado, Mateus Hostert, Ivan Esteban, Ivan Martinez, and Huber Perez Gonzalez, and Kevin Kelly. So it's a rather long list of authors. That's mainly because we had to do it fast, so we needed all the people power we could get. And here's the result. So the horizontal axis in this plot is once again this effective mixing angle that would describe the short baseline mu-neutrino to electron-neutrino conversion. The vertical axis is again the mass squared difference, which is a measure for the oscillation length. The gray region that I'm showing here is from mini-boon, and the blue and orange contours are exclusion limits from two of the microboon searches I showed on the previous slide. The blue one here corresponds to the 1EX search, so the inclusive single electron search on the right. The orange curve corresponds here to the 1E1P CCQE analysis. So you see that the inclusive one is more sensitive, and while it does not conclusively rule out all of the mini-boon allowed region, at least not at the 3 sigma level that we are shown here, it significantly constrains the possibility that the mini-boon anomaly is in fact due to real mu to mu-e conversion. Yeah, and let me emphasize again, what we are showing here are 3 sigma exclusion limits. So in a sense, that's a rather conservative plot. If you did this at 2 sigma, then there would be marginal overlap between the 2 sigma region allowed by microboon and the 2 sigma region allowed by mini-boon. And so if you compare the two directly, 2 sigma by 2 sigma is definitely worse than 3 sigma. So there's really significant tension between what mini-boon sees and what microboon does not see. We'll get more conclusive answers in the future. The purple dashed line here is the 3 sigma sensitivity of the full short baseline neutrino program that's unfolding at Fermilab at the moment. This will consist not only of microboon, but also of 2 additional detectors, namely SBND and Icarus. And those will weigh in with more statistics, with yet 2 different baselines, and will then give us a more conclusive answer. But even right now, I think it's already fairly clear that mini-boon is not just mu to mu oscillations. So what else could it be? What else could and should microboon be looking for in the future? I already mentioned that what we really need is an inclusive single photon search, which would be sensitive, for instance, to a new particle decaying to a photon. So I haven't talked much about new physics, and I won't talk much about new physics other than vanilla sterile neutrino oscillations in this talk. But there is a number of very, very interesting papers that propose models typically involving heavier sterile neutrinos in one way or another, and then invoking not oscillations, but the decays of those heavier particles. So for instance, if you make a heavy sterile neutrino, either directly in your detector in a neutrino scattering event, or already in your target, then that heavy particle might decay back to a standard model neutrino and a photon. This would give a high energy single photon that could mimic the mini-boon access and would not have shown up in any of the existing microboon searches. So it's paramount that microboon should do this search, and of course microboon will do this search. Another possibility is a search for boosted E+ E- pairs. Remember, to mini-boon, any kind of electromagnetic shower looks exactly the same. So if you have 2 rather collimated electron, if you have an electron and a positron that are rather collimated to mini-boon, this will again look like a single electromagnetic shower. Now, where could such a boosted E+ E- pair come from? Well, it could come, for instance, from the decay of a dark photon. And a dark photon could again come from the decay of another heavy sterile particle. So many of these models that are being discussed in the context of intensity frontier physics around the 100 MeV to GeV scale or so. There's a number of viable models at that scale that could in principle explain the mini-boon anomaly while being consistent, maybe not with the other short baseline neutrino anomalies, but at least being consistent with all the null results that are out there. Coming back to the possibility of pure sterile neutrinos, to put yet another nail in the coffin of that hypothesis, let me show this slightly outdated plot, which is from our last global fit from 2018. We haven't redone the global fit since then because it was already quite conclusive with the data available then, and the conclusions would only have been reinforced since. So this is now a slightly different parameter space, namely what's shown here on the horizontal axis is the mixing between the hypothetical sterile neutrino and muon neutrinos. Remember, the signal that we are looking for in mini-boon is muon neutrino to electron neutrino conversion. But for a sterile neutrino to do this, it needs to mix both with the muon neutrino and with the electron neutrino. And the reason I'm showing specifically the mixing with the muon neutrino here is that that's the one that's most tightly constrained by other searches. So in this plane here, if we believe in the short baseline anomalies, then we would end up somewhere in these bright red parameter regions here. But then if we look at the non-anomalous results on muon neutrino to sterile neutrino conversion, and combining all of them gives the black curve here. So the region to the left of the black curve is allowed. The region to the right of the black curve is ruled out at the 99% confidence level. So as you can see, there's really significant tension between this exclusion limit and the parameter region that would be required to explain the anomalies. We can quantify this and we come up with a very small p-value of less than 10 to the minus 4. So what does this mean for the future? Well, of course, this means we have to further scrutinize the anomalies for unknown systematics. But let me remind you that there's 4 unresolved anomalies at the moment. And these experiments that gave those anomalies have very little in common. So in order to explain them without new physics, we'd probably need 4 completely independent facts. On the other hand, I think it's always good to scrutinize anomalies, but sometimes it's also good to scrutinize null results. Now, in this particular case, I don't have anything to say about those null results. I think they're all fine. I don't have anywhere where I could point my finger where there could be a problem with them. So I think they stand and they are robust. But in general, when we try to resolve an anomaly, I think it's always a good idea to also scrutinize the null results. Okay, so let me summarize now so that we still have some time for discussion. I've talked about 5 different anomalies. The first one was based on neutrino flux measurements from a nuclear reactor. This flux appeared to be too low for quite some time, but that anomaly has now been resolved. There's still a bit of an anomaly in some of the reactor neutrino spectra that still needs to be resolved. There is the so-called Gallium anomaly, which is based on measurements of neutrino fluxes from intense radioactive sources. And that anomaly, in fact, has recently been reinforced. So there, we should maybe really start taking this more seriously. There is the LSND anomaly. There, I haven't seen any proposals for what could be the origin for quite some time. So at the moment, it still stands at 3 sigma and is unresolved. The mini-boon anomaly is also still unresolved, but there we are seeing significant progress right now. So microboon has already weighed in big time. Microboon has in particular disfavored an explanation of the mini-boon anomaly in terms of delta resonance decays. That was previously perhaps in my opinion, one of the most likely explanations for the anomaly. Now it isn't anymore. But the good news is microboon is by no means done yet analyzing the data. There are the upcoming short baseline experiments. And so with those, there's now real hope that we'll ultimately get to the bottom of the mini-boon anomaly in the not too distant future. So let me thank you for your attention, and I'm happy to answer questions.
Thank you. Thank you, Joachim. I see some people are clapping in the audience. So we open the floor for questions. Feel free to raise your hands or unmute yourselves directly. I have some questions, actually. Sure. I wanted to see if there were, maybe people are a little bit shy. Well, one of the things, I have a comment and then a question. So a comment regarding the gallium anomaly is that it's a little bit hidden in the best paper, but if you look carefully, and actually we did an analysis of the data, so we did our own fit in a latest paper with Thomas and with Patrick. Yeah, the anomaly is now at 5 sigma. It's more than 5 sigma.
Yeah, right. Yeah, I should have mentioned that. I apologize.
So it's a little bit puzzling, no? Because this anomaly is in strong tension with the solar neutrinos. Solar neutrinos do not see anything. So I don't know what's your take on this, if you have thought about this, what kind of possible way to reconcile these two would be there, no?
So in fact, we have thought about it a bit. So my first reaction when I saw the best result was, okay, now let's take this at face value and let's assume that our measurements of the solar neutrinos at low energies are just different, because these are the only experiments, the gallium experiments are the only ones that can see the solar PP flux. So what if it's just that the solar PP flux is different? Then the solar neutrino rate could be modified while leaving all the solar neutrino measurements at higher energies unchanged. Now, I looked a bit deeper into this, and of course, I found that Concha Gonzalez-Garcia has looked at this more than 10 years ago with her collaborators. And it turns out that all of this appears to be rather robust. So changing the solar PP neutrino flux by the amount required here is really a no-go in all the solar models that are on the market. I'm aware that there is some uncertainty in the solar models, especially because of this question about solar metallicities, right? There's different measurements of the solar metallicity that disagree with one another. But depending on what metallicity you believe in, this affects the fluxes at higher energies in some way, but not the PP neutrino flux. And it's to be impossible to come up with a good fit to solar neutrinos if you take the best result at face value. Now, in that paper by Concha et al. 10 years ago, of course, they didn't have the best result yet, but they already had the other results that gave the previous gallium anomaly. And they asked the question, well, what if you take that at face value? What would it do to the solar fit? And the conclusion was, it leads to inconsistency. So it can't be easily reconciled.
I see. Sorry, my connection is fading a little bit.
Is it yours or mine?
If I lose it, then
is it yours or mine?
Someone take over. Hello?
Yeah, we lost connection again. I think it's in the whole institute, unfortunately.
I think it's the, okay. I wasn't sure if it was just me.
Yeah, it was just at the very end. I mean, I could follow all your talk, but it was just now in the questions that it is intermittently going on and off.
Okay.
Yeah, I got a message from Zoom saying your connection is unstable, so I thought it was a problem on my end.
No, I think it's a problem on our end.
Okay, yeah. So what I was saying is I was talking about this 2010 paper, I think by Concha et al.
Yes.
Where they discuss this in the context of the old gallium measurements and come to the conclusion that it's really hard to reconcile all our knowledge about solar neutrinos with that anomaly.
Yes,
so
you were.
Yeah.
Yes, sorry, you were mentioning the PP flux, but the PP flux is measured by Borexino, no?
Yeah, by now the PP flux is actually even measured by Borexino rather precisely. So when I did the comparison, the Borexino measurement became even more impressive to me than it was before. So we have that, and also the solar modeling allows for relatively little wiggle room in the PP flux, because the PP flux is directly related to the solar luminosity, which we see. Because it's the dominant energy source, so any energy that's produced in the PP cycle has to get out of the sun somehow. So that's what makes for its luminosity. So there's very little wiggle room there. So the only possibility would be to somehow play with the fluxes at higher energies and then try to adapt the best fit mixing angle. But all of that appears not to work really well.
Okay.
So, yeah. There was at the time, there was some discussion about the cross sections for this neutrino capture reaction on gallium, and people were aware that there were some uncertainties. But I haven't seen any recent news.
We looked a little bit onto those, and even if you are super conservative and you take like it's really not enough, not working. Yeah. No, it's not enough to make it work. At least for the best, especially for the best result. The puzzling thing about the best result is that, as you said, no, they took data in these two different volumes, but they got the same rate. So it's an overall deficit, again, that is not really clear where it's coming from. It's very puzzling.
Yeah, I fully agree.
Yeah, okay. Are there any other questions?
I don't have a question on the talk, which was very clear. But since no one is asking, I wanted to know because I mean, I know that well, as you explained, the sterile neutrino interpretation of the mini-boon, etc., anomaly is in quite tension. There are all these other alternatives. You went very fast over some possibility. All of them have their own things. So I was just wondering if you have a favorite one, which one it is.
It's hard to say. I'm kind of following all of them, and I find all of them rather interesting. I mean, the thing is, almost all of them would be explanations for the mini-boon anomaly alone. They could not weigh in on the other anomalies. I thought for a while that heavy sterile neutrinos decaying to light electroneutrinos could do that. But that also doesn't really work. That would then be in tension with solar neutrino measurements. Now, the two that I mentioned, heavy sterile neutrino decay to a photon or a dark photon, I think they are still alive and kicking. There's one slight issue with these decaying sterile neutrino explanations, and that's that they typically predict event spectra that are more boosted in the forward direction. Now, that's not really a big tension with the mini-boon data, but it's something to keep in mind. But I think it's still perfectly okay. also depending on where exactly you put the masses of the particles involved there, you can make the spectrum more isotropic. So I'm not saying that this is by any means rules it out, but yeah, that's kind of the direction that this appears to be going. Also because these are typically models that fare much better in cosmology than the light sterile neutrinos do, for instance. But I couldn't really pick out one all-time favorite among the many models.
Fair enough.
I see that Manu has a question.
Yes, can you hear me?
Yes,
Yes.
loud and clearly.
Okay, so thanks for the talk, Joachim. It was very nice. So I don't think you mentioned the Neutrino Anomaly. Correct me if I missed it.
I did not mention the Neutrino Anomaly because I thought that had been resolved at some point.
Okay, so
I
no, I just wanted to know your opinion on it because we hadn't seen how it was resolved, and we knew that it stood for like 20 years or something like that, and that it wasn't particularly famous compared to these anomalies you were mentioning. So I just wanted to know your take on this.
So I remember a paper maybe 5 years ago, maybe 10 years ago, that claimed to resolve the Neutrino anomaly, and to my layperson's mind, what they did there sounded quite reasonable. I don't remember the details. It was just like a more precise theory calculation, but I really don't remember the details. I can look up the reference later if you want.
Okay. Yeah, I remember there were some early explanations to that based on supersymmetry, but I think there was nothing quite recent.
Yeah.
Yeah, I will look at it.
Yeah, there was this paper that claimed to resolve it, and since I didn't see any more papers on the Neutrino anomaly after that, I assumed that that was kind of consensus in the community that that is now resolved. But I'm happy to be proven wrong on this. As I said, I'm never looked much into the detailed standard model physics behind the Neutrino anomaly, so I'm not really in a good position to judge. But yeah, thanks for pointing this out.
Thanks a lot.
Yes, regarding this, well, I should also point out that there are several Neutrino anomalies. No, I guess that Manu is talking about the one on heavy neutral leptons.
Yeah, I think you were referring to different anomalies.
The dimuon.
Yeah, the dimuon Neutrino anomaly, where there would be asymmetry in the energies of the muon pair. Yeah.
Yes. Yes, coming back to the issue of explaining mini-boon with non-minimal models, I think also the challenging thing is the elephant in the room, no, LSND, which so far as I know, I don't know if Joachim, maybe you know the literature a little bit better, but none of those models is able to explain LSND. LSND would be something on its own, and people.
Right. Yeah, that's what I meant when I said they are focusing on the mini-boon anomaly. So for a while we thought that by having a heavy sterile neutrino decay to electron neutrinos in flight, and then using those electron neutrinos as an actual signal, that could explain the LSND anomaly. But then it was pointed out by Matthias Hostert and Maxim Pospelov and others that we had underestimated the constraint from solar neutrinos.
Yes.
So with that constraint taken into account, explaining LSND and mini-boon simultaneously appears to no longer work. Doing mini-boon alone, I think, is still okay, but doing LSND and mini-boon together is now again impossible, simply because the baseline is so incredibly short that you need really, really large coupling constants or really large mixing angles to make all of this happen sufficiently fast.
Very good. So
yeah, that's the thing is, LSND has this rather unique signature from inverse beta decay. They see an electron and a neutron, and that's really, really hard to mimic with anything other than a real electron antineutrino. For instance, for a while I thought that it could be possible to explain LSND with interactions of not electron antineutrinos, but electron neutrinos, of which there are many in the beam. So the idea would be an electron neutrino comes in, and it doesn't produce a neutron, but it produces a proton. Now, on its way out of the nucleus, that proton could hit a neutron and kick out the neutron. So you could get an electron and a neutron from such an event. And in fact, those events do exist. But if you look at the detailed energetics, they are too low in energy to pass the LSND cuts.
I see.
So in that sense, they did a fairly robust job. There was for a long time, people have speculated that pion decays in flight could explain LSND. So LSND really only works because they have this stopped pion source, and stopped pions are all of the same sign, so they do not make electron antineutrinos. But if you have a pion that decays in flight, this can be pions of either sign, and so you get a small background flux of electron antineutrinos. And people have looked into that in quite some detail, trying to see if there was any mismodeling of this decay in flight contribution. But the current state of the art is that we don't see what could have been wrong there.
Yes, I see. Well, okay. I don't see any more raised hands. So thank you again very much, Joachim, for this very nice talk.
Well, thank you for attending and for the discussion.
Let's pause for lunch. Let's give us a break, and we resume at 3:30. Okay?
Okay. See you then.
Bye-bye.
Bye-bye.
Bye.
Thanks a lot, everyone. Bye-bye.